This quick video lesson will summarize Dalton's law of partial pressures and how we will apply it to a couple of mini labs that we'll do in class. So first of all, Dalton's law of partial pressure says this: that pressure of a gas in a mixture of gases would be the same as if it were alone in a container. That's a really awkward definition. I kind of like this definition a little bit better. That says the total pressure in a mixture of gases is equal to the sum of the individual pressures. And that's a little easier to understand, also easier mathematically to understand. So, for example, the air that you breathe is 80% nitrogen molecules and roughly 20% oxygen molecules. And if it's one atmosphere, that means when you inhale, you're taking a breath that is exerting 0.8 atmospheres of nitrogen because it's 80% nitrogen molecules and 20% oxygen molecules. So it would be 0.2 atmospheres for the nitrogen. That picture shown down here, if you have half a mole of hydrogen exerting 2.4 atmospheres and 1.25 moles of helium is exerting 6 atmospheres of pressure, you put them together and they exert a total pressure which is summative, right? It's additive. So interestingly and important, is this nugget right here. Pressure ratio is equal to the mole ratio. So if this mixture is, let's say, 75% helium, it's going to exert 75% of the total pressure. All right, makes sense. Another thing to note about Dalton's law is that it makes no difference what particles are present. The identity doesn't matter. The total pressure of a mixture of gases is only dependent on the total number of particles present, number of moles. So we've got 3 different gases down here at the same volume and temperature. Some mixtures and some pure gases, but they all exert the same pressure because they all have the same number of moles, same number of particles. So why do we care? Why is this simple little law important? Well, primarily because, let me just, undo that. Primarily because we use this in experimentation to collect gases. Gases are finicky and hard to collect. And so we use a method called water displacement, where we will bubble gases up into a filled container filled with water. And you saw this in one of your lab experiments earlier this week. And the air or the gas collected will bubble and force the water out, and you can collect and measure a volume. So what's shown here is this reaction down here. Let me move down. I'm having trouble with my markers, so bear with me. Take a look at this decomposition reaction down here. It's potassium chlorate under heat, so that's shown with the Bunsen burner right there. If you heat it up, it'll drive off oxygen gas. The way to collect that, again, is by water displacement. You fill up an inverted graduated cylinder, and then the gas bubbles up. Sorry about that. The gas bubbles up, and you can measure a volume of that gas collected. So the problem is this: it doesn't just contain pure oxygen. At any temperature, water vapor evaporates. You guys know this in DC when we have those hot, humid days. The warmer it is, the higher the temperature, the more water vapor air can hold. So this gas that we've collected is not pure oxygen. It includes water vapor, and that's an error, and it can be an error of 3 to 5%. So how do we get rid of that? To determine the pressure of oxygen, then we have to subtract out the water vapor pressure, and that's using Dalton's law of partial pressures. So how the heck do we magically pull out the pressure exerted by an individual gas from a mixture of gases? Well, luckily for water vapor, it's easy because we know the pressure exerted by water at every individual temperature. It's called the vapor pressure. And as you can see from this chart on the left, that as the temperature increases, the vapor pressure of water increases. And again, just like in DC, we know this. When it's hot and humid, it's because air at high temperatures can hold more water vapor than at low temperatures. And we feel that. So you can even look up numbers. If you just simply take the temperature, you will know the vapor pressure exerted by water. And here's an example of one of these vapor pressure of water tables I pulled off the internet just a few minutes ago. So we can see any temperature, we can find the vapor pressure of water. So here's how we'll use this in the lab. We'll do an experiment something like this. Let's say we collect 6.2 liters of oxygen gas, and we collect it by water displacement and at 25 degrees C and 1.02 atmospheres. What's the mass of oxygen collected? So if it's mass, then we know we have to solve for N from Puvnert, for number of moles, and then convert to mass. And notice we are definitely not at standard temperature and pressure here. So we have to use Puvnert to solve this problem. So I've shortened things. There's again is our decomposition reaction. And I've written in a few variables. The pressure, the total pressure is 1.02 atmospheres. That's written there. The pressure of the water, though, is something we can look up. So 25 degrees C, what's the pressure of water vapor? Let's go back here and say, hey, there's 25 degrees C. Oh, it's 3.2 kilopascals. What the? That's the only table I could find online on short notice was one on kilopascals. So we have to convert to atmospheres. I'd give you this conversion on any test or quiz, but essentially it's dividing by 100. So 3.2 divided by 100 is 0.032 atmospheres. So at 25 degrees C, oxygen exerts, bear with me, let me change the color of my pen, 0.25 atmospheres. And then using Dalton's law of partial pressures, we can, Dalton's law of partial pressure says, okay, we collected that. Let me go back to 2 slides. We collected that volume of gas right here. What part of that is water vapor? Well, that's what we'll do right now. So the total pressure is equal to the oxygen, which is most of that gas, and a little bit of water vapor in there. So let's rearrange this and just solve for the pressure of the oxygen, which is the total pressure minus the atmospheric pressure. So we have total pressure is 1.02 minus the the water vapor pressure, which is 0.25. And I think it comes out to be 0.988 roughly. Yeah, I think that's right, rounded. All right, and then notice we've got all the things we need in Puvnert to solve for N, which is shown right here. We've got pressure of the oxygen gas. We subtracted out the pressure exerted by the water vapor. We've got the volume and we've got the temperature. So we just Puvnert it real quick to get the answer. And the answer is in N, we have 0.25 moles of oxygen gas. So we need to convert that to mass because the question asked, again, what mass of oxygen is collected. And that's at 32 grams per mole. And this is 0.25 times 32. So the mass is equal to 8.0 grams of oxygen gas. And that's really all there is to know about Dalton's law of partial pressure. So good luck, and I will talk to you soon.